In this programming example, we will implement an encoder-decoder network for neural machine translation using TensorFlow. This is a fairly complicated example compared to what we have seen before. So maybe you will have to spend some time looking at the code, trying it out to really understand it. So we usually start with importing the modules that we are going to use. Note that we are importing this RMS prop, which is a different optimizer than Adam, which turns out that it works better in this example. Then we define a number of constants, like 20 epochs, and we have a batch size of 128, and other constants, for example, to limit ourselves to reading 16,000 example. And this piece of code to get access to Google Colab, and you can download the data from this link and add the path to your data in this source destination file name. So we will do that, and we will have the training data will be the R, which Arabic.txt. It has the translation from Arabic to English. It has a sentence in Arabic and a corresponding sentence in English. This function to read the file, and then we split it into a pair of the source sequences and destination word sequences. And then we return the source word sequences and the destination word sequences. We also need to tokenize and untokenize words. So we have this function to do that. We are declaring this tokenize that we will then use so that we can transform a sequence of word into indices, and then we can go into the other directions as well to tokenize. We are going to use start and stop tokens. So we want this network to tell us when it's done translating a sentence. We are basically going to provide it with a sentence in one language, and then we give it a start token. And then the start token is the indication that it's supposed to start translating and provide the translation of that sentence, but in a different language. And then it's going to start emitting a number of words until it's done with the sentence, and it will indicate that it's done with the sentence by emitting stop token. So we'll create our training so that the sequence starts with a start token and then ends with a stop token. And then we will teach the model that it should always emit a stop token at the end of a sentence. So those are helpers that we are going to use. Then we call the read file combined that will give us the source sequence, so that's in Arabic, and then the destination, which is in English. And then we will tokenize these. So this tokenize method provides both a tokenized itself, and we are going to use later, and then also the tokenized sequences. Then we do another tokenize. This is in English. We are going to tokenize the destination. So now we have a destination tokenize and the tokenized sentence in English. And this, if you want to have a look at the tokenized and the sequence of the word. Then we need to prepare the training data in a format that works for this model. So if we start with what we want from the decoder to actually produce the this target token sequence. So for the destination, we have the this token sequence that the sentence in English. we do that for X. We are going to basically list all the words in a sentence and then we append it with stop index to the end. So that's how we are going to teach the model to not only produce the translation, but also produce then the stop index so that we know when it's done producing this sentence. In terms of the inputs to this decoder, we wanted to get kind of the same inputs but shifted in time. So at the first time steps, we will have this decoder, which will be initialized with a state, the intermediate state from the encoder. And then we will give it a start index token. So that's the first time step. The input it gets is a start token, and then we want to produce the first word in English. And then we are going to take that word and read it back using autoregression. So that's why we see here on the input to the decoder, we will also look through this destination target token sequence. So that's the same sequence as we just prepared, but we will also prepend it with the start index. And for the source input data, so this is what we are providing to the encoder. So this is going to be the Arabic, the sentence in Arabic. And here we are just going to pad that so they all have the same length. So this is going to be our source input data. And we don't need to do anything special. And then we take the thing that we just had prepared, the destination input token sequence, and we are padding that so they also, all the sentences have the same length. And padding post here means that we are adding zeros to the end of the sequence. And then for the output, we are going to pad it at the end, and we are going to do the same thing with the destination target token data. We are also doing a padding, so all this to prepare the training data. Then once we have these training data, we want to split it into the training and test set. So we will do that here in this piece of code. For the test set, here we take the total number of the rows times that test percent, and then we are randomly pulling a number of examples to become our best indices. And our remaining ones are the training data. And we then actually pull out those from the arrays with this. So we have the training indices. So this is for the source destination, both the input and the target data. So now we created that as for the training dataset. We have the remaining one for the test dataset. Now another thing we are going to do is in order to get a feeling of how the translation is working, we want to inspect some examples manually. We are going to create a smaller list of examples. We are going to take a subset of test examples and then to print out the translations. We define the this sample size to be 20. And we are going to take this 20 example from our test data and inspect it in more detail. We are just storing them in these variable indices. So all of this kind of data preparation, has nothing to do with the model itself, but it's a big part of the work to make sure that we have the training data with the correct format and for the test set as well. Now let's go and build the model. In the past videos, we have built models using the Keras sequential API because all the models we have done has simply been stacking a number of layers on top of each other. But now we are building this encoder-decoder model, which we will use for it the Keras functional API. Using this API, we declare the layers separately, and then we have a separate step where we connect them together. In the sequential API, we both declared them and connected them at the same time because they were basically you connected a layer to the one that you had declared before. So it was just implicit connecting them after each other. But that's not the case with the functional API. So what we start with is to declare all the layers we want, and we need to also explicitly declare the inputs. So we have the encode embedding input, and we will actually be starting with just building the encoder model. So it's going to have an input, which is the embedding that we are presenting to it, and then we are going to have embedding layer, and its output dimension will be the width of the embedding, and the input dimension will be the maximum number of the word in the vocabulary. And we are going to have one encoder layer. The first encoder layer is LSTM. We want that one to be return sequences equals to true. We also wanted to have return state equals to true. So it will not only output of the layer, but it will also output the internal cell state. And then we have a second layer. So our encoder model is an embedding layer followed by two LSTM layers. Now we need to connect these layers together. So we see here, we take the embedding layer, the enc embedding layer, and call that with the inputs to the embedding, enc embedding input. So that's how we connect this input layer to the embedding layer. And the output of this is the enc embedding layer output. And we are going to then use those output as the input to the first LSTM. And we see this call to the first LSTM enc layer 1 will produce a number of outputs here. Enc layer 1 outputs, enc layer 1 state H, and also the C state. So then we are calling the next LSTM, and it will take the outputs of this first layer, this one, the outputs, and that feeds that to the second layer. And this is how we connect the different layers together into a model. Once we have done with that, we are going to create an actual model from this. And we do that by stating that we want to build a model that's followed by two arguments. One is the inputs to the model, which is the encoder, embedding input, and the next argument is the output from this model. And the output from this model is a list of the following variables. So we can see that it will output the H state and the C state for the first LSTM layer, as well as the second LSTM layer. And we need that as output because that's what we are going to use then as input to the decoder model. So this is our entire encoder model, and we can print out the model by using the .summary method. So you can see here our input layer, we have our embedding layer, and then we have one LSTM and the second LSTM. Now let's talk about the decoder, which will have more inputs because it will not only have the embedding input, but it will also have the initial internal state. So we will have H and C input for the first LSTM, as well as the H and C for the second LSTM. So here we create these decoder layers, we create the embedding layer, we create the LSTM layers, and then the decoder model will finally consists of the fully connected layer with softmax on the top. So the encoder, we just embedding, and then with two LSTM layers, the decoder is an embedding layer, two LSTM layer, and the fully connected layer. So we are using the functional API here. This is just to declare the layers. We need to connect these layers together. So for the decoder embedding layer, we connect that to the input, and we take the output of this embedding layer and we provide that to the input of the first LSTM. But here we do something else as well. We say that the initial state for this layer should be taken from the H and C. So this is how it transfers the state from the encoder model to the decoder model during this time step. We do the same for the decoder layer 2, so that the second LSTM layer, it's going to get its input from the output of the previous layer, and again its initial state should be taken from the encoder. We are going to supply this explicitly as inputs to the model, and finally we have our outputs, which takes the output of the second layer, LSTM, as input and produces this outputs. Now, looking at this model takes as the input both the decoder embedding input as well as the initial state that was supplied from the encoder. But then it also produces as outputs not only the output of the top layer, which is decoder layer 3 output, it also produces the H and C state for both layers. So this is going to be used in auto regression later. We are going to call this model, we are going to supply it with the start token, as well as the input state from the encoder, and that's going to produce the first predicted word. We are going to then that word as well as the output state to feed that back in the next time step. We are going to take that state as input to the model and the predicted word as input to the embedding. And that's going to give us the next one. And we are going to do that in auto-regressive manner until the model predicts a stop token. That's when it's done translating. And now let's print the summary of the model. As you can see, we have the inputs layer and including this input layer and the embedding layer, other input layers that are the states. We have an LSTM, the input layers to other LSTM, which is the state for them, and we have LSTM, and then we have the final output layer. Now let's talk about the training process. Now we have an encoder model, we have a decoder model. We want to combine them into the full model that we can use for training. We have the encoder embedding layer, embedding, encoding embedding input, and the decoder embedding input for this training model. And then we are going to get an intermediate state which is coming from the encoder model. So this is the intermediate state coming from the encoder model. And here is how we are now connecting things together. We are saying that the decoder model will, as input, its input have the training decoder embedding input, and it will also receive the intermediate state as inputs. Then from that, we can build the final training model, and the training model has two inputs. It's the embedding for the encoder, the embedding for the decoder, and then it's producing output from the decoder. And as an optimizer, we want to use the RMS probe. We want to use something known as sparse categorical cross entropy. It's technically the same thing as categorical cross entropy, but we don't need to actually describe the outputs as one hot encoded. We will instead describe this as the index that we are trying to predict. This is really just for memory optimization. So we don't have to have a big training data, because when we do a one hot encoding, you are just going to have a lot of zeros. And if you have a fairly big vocabulary and a lot of training examples, that's going to take up a lot of memory. So using this sparse categorical cross entropy will reduce the need for memory in the model. And then we print out the summary of the model. We see that we have our model with these two input layers. Then we have our encoder model and our decoder model. Now we are ready to train and test this model. So what we will do, let's jump to the code. So what we will do is that we will train it for one epoch, and then we will inspect these 20 examples to see how it results. And then we will do another training for one epoch. The outer loop will run for a number of epochs, and then we call the fit function here. We will just say train for one epoch, and then we will call it this fit function repeatedly. So this training model has fit method, where we say that the input here is now a list, which this list has both the source input and the destination input data. So this is both for Arabic and language and the English sentences. And then we have the destination data, which is the output. And the same thing with the validation. We do with the same thing with the validation data right here. We have a list of input and then the output side, and also the batch size. So this will train the model for one epoch. Let's talk about the first inner loop. We have two loops here. The first one, what we are doing here, we are going to use this model on some of these test examples and see what translations it will produce. And that's also a manual process where we are going to use auto regression. So this is the first inner loop. We are looping through these 20 examples. So we are taking out one sample input data, this one, and then the sample target data. So this is basically one Arabic sentence and one English sentence. And then we are taking the Arabic sentence and run through the encoder model. This one, encoder model.predict. So here, when we do this auto regression, we are not using the joint model. We are going to use the split encoder and decoder model separately. So we start running it through the encoder model to get the intermediate state, which is here the last states that one produces. That's all we need from the encoder model. And now we can start doing auto-regression with a decoder model. Here, this is the part of the decoder. We are going to present the decoder model with this state, the last states, and we are going to initialize it with the state and to give it the start index. This is the last states, which is the start token that tells the intermediate state to start translating into English. So it's going to have the intermediate state, will describe what is the overall meaning of the sentence, and then it's going to generate the first word in English for that sentence. Then we are going to take that word, feed it back in the next step, and it's going to generate the next one, and we will do that until it predicts a stop token. It might not actually predict a stop token, so then we will stop automatically. If we have predicted too many words, so here we have a maximum number to stop. So here we have if statement. If previous word index equals to stop index, then break. And otherwise, it will stop after max length, this one, after max length of words. So here we can see how we can use the decoder model. This one here, the model.predict. And we do a prediction, and the output from this model will be these are the predicted words, and it will also output its internal state. And those internal states we are going later to use as the input to the model, again because we need to initialize this with the next set of states that it has produced. So we see the call of dec model.predict to the decoder model. We take list of consisting of the input word x, then we concatenate that with these states. The last states is a list of these 4 variables. So each time we call predict, we read out the states and we get prediction, and then we do the argmax to find what is the actual word that it has the highest probability. And then we put that into predicted word sequence so that we are going to use to print it out later. So then we can take these inputs and what the targets should be, as well as the predicted targets, and we do convert that to words. So we can then print them out. So each of these print out the corresponding sentence. This is the Arabic sentence, and this is the true English sentence, and this is the sentence that the model predicted. So if we have a look at the output of the training process, it will take a lot of time. So for example, this is the Arabic language word by word. لدي وظيفة جيدة الآن. And this is the true English. I have a good job now. And the predicted is I have a good idea now. The more epics you have, the more accurate results you will get. For example, let's have a look at this. التذكرة من فضلك. And this is the true English. Ticket, please. And this is the predicted. Please turn out. So you can play with the code and see the results. All in all, we can see that with the relatively simple code, we can produce a network that can do some translation between Arabic and English using TensorFlow.